Welcome back to class. In this lesson, we will introduce the magnetic circuit. We will see the basic properties of a magnet, and at the end of the lesson, I'll use a work example to help you understand how to calculate the magnetic flux density. That said, let's get into class. The magnet itself is a ferromagnetic material with properties of attracting other pieces of material like itself. Now, these ferromagnetic materials are diverse materials which can include the iron, the nickel, or cobalt. Now, all around this magnet, there are magnetic fields. This magnetic field is actually the area around the magnet. It is in this area that the magnetic field is felt. Now, another unique thing you must know about the magnet are its two poles, that is, the North Pole and the South Pole. Here is a typical example where you have the North Pole being placed together. When North poles are placed together, they repel each other. But when North Pole is placed against the South Pole, they tend to what? To attract each other. Around this, from the north to the south, obviously there are magnetic fields. And this is where you have your magnetic fields from the north to the south. This magnetic field actually produces magnetic per unit area is called magnetic flux density. Mathematically, I can represent my magnetic flux density be equals to magnetic flux over area. In most textbooks, you see magnetic flux being represented as phi, area represented as A, and magnetic flux density represented as B. Now for unit, the unit of your magnetic flux is the same thing as Weber. Now shorted as WB. The unit of my area, as usual, is always meter squared. And the unit of my magnetic flux density is always Tesla, shorted as T. Now, but one unique thing you must observe is that 1 Tesla is the same thing as 1 Weber per meter squared. Let's take some example. First example says that a magnetic pole face has a rectangular section having dimensions 200 mm by 100 mm. If the total flux emerging from the pole is 150 Weber, that means my file is the same thing as 150 Weber, and my area from this place, my area should be given as 200 mm times 100 mm. So that my file now, my area will be the same thing as 20,000 mm. Now my Tesla, my flux density, if the total flux emerging from the pool is 150 Weber, calculate the flux density. That is, my flux density B is given as phi over E, which will be equals to 150 Weber divided by 20,000 millimeter squared. I've decided to leave this in millimeter square. And so this is equals to 150 cancels 1. So I have 2. 2 here, I'll be left with 1,000. 2 in 15 will be 7.5. So I'll leave this as 7.5 times 10 raised to the power minus 3 Weber per millimeter square. So we're leaving our measurement in millimeter square and we're stating it out. Now, let's see the second question. Our second question states that the maximum working flux density of a lifting electromagnet is 1.8 Tesla. That's the density B is equal to 1.8 Tesla. And the effective area of the cross section, and the effective area of a pole face is circular in cross-sectional area. That means what we're dealing with here is a circle, and my area will come from pi r squared. If the total magnetic flux produced is 353 milliweber, determine the radius. Then I'm to determine the radius, that's r. Now we know that B is equals to phi over E. Here we've been given B to be 1.8, will be the same thing as phi, which will be 353 times 10 raised to the power minus 3 over area E. So that my area E now will come from 353 times 10 raised to the power minus 3 over 1.8. That's the same thing as 0.196. Now, if area E is equals to 0.196, that tells me that pi r squared is equals to 0.196. R squared will be equals to 0.196 over pi. Obviously, r will be equals to the square root of 0.196 over pi. We know that pi is equals to 3.14. That's 0.196 divided by 0.2498. That's approximately 0.25 meters. Thank you for staying with us. In our next lesson, we'll see magnetomotive force, reluctance, and other concepts. Thank you, and see you in our next class.